So our next presenters are Zoe Conroy and Yuri Mitnick from Cisco. Yuri is a component engineer who's focused on ASIC quality, reliability, and product engineering. And prior to Cisco, he was at Intel, PDF Solutions, and Qualcomm, where he worked cross-functionally across the product lifecycle, including DFX activities, ramp-up, characterization, test infrastructure, manufacturing process, the usual list of cross-functional challenges of getting product out. Yuri received a Bachelor and Master's of Science degree in Electrical Engineering from Technion Israel Institute of Technology. Zoe is currently the Senior Manager of DFT and Test in the Component Quality and Technology Group at Cisco. And she spends a lot of her time working cross-functionally on component quality issues, all the way from silicon ATE level testing all the way up to the system level. And this gives her a lot of insight into the challenges of making sure that everything is correct, and challenges of test and quality, and closing gaps in the supply chain. Prior to Cisco, Zoe was in a number of different roles at Procket Networks, Agilent Technologies, Hewlett Packard, and Wolfson Microelectronics. She has a Bachelor's of Science degree and a PhD in Electronics and Electrical Engineering from the University of Edinburgh. It is a great pleasure to welcome Zoe and Yuri. And as I mentioned, we will make the slides available by next week, and the videos will be available on YouTube. So with that, we'll also do an interactive presentation. Zoe, it's all yours.
Thank you, Ira, for the introduction. And thank you, David, for a very interesting talk. I definitely, a lot of synergies with what we're going to talk about today. So it's a good segue into our presentation. So we're going to talk about design diagnosis and the digitization for efficient system test and analytics to accelerate time to quality across the end-to-end value chain. And myself and Yuri will be talking today. And as Ira said, we're actually partners in the Component Quality and Technology Group at Cisco. So our areas of discussion today will look at the life of a known good die over the end-to-end value chain. And specifically, where can known good die start to become known bad die as they get integrated into a system? And why does that happen? And then clearly, once you found out that a die becomes bad, it's like, how do I alleviate that problem? So then we talk about orchestrating across multiple domains, of really, understanding what happens to that die as it goes down subsequent test steps into the final product release. We talk about facilitating co-optimization with other components that die will be interfaced to and integrated with. And then the value of extending characterization beyond what is done at ATE characterization early in the product's life. And then what results can you expect from all of this? And then we'll touch on some end-to-end analytics at the end. So our main sort of thesis here is that you test for something known good at any point in your end-to-end test flow. But at some point, there's a chance that what is known good will become known bad. And that can mean many things. The subject today is around known good die, but really as that die gets integrated down the end-to-end flow or the value chain, many things start to happen to it. So you start with your known good die. The die will come into a stack. You then probably test for a known good stack. The stack would go into a package or a module, or you may have several heterogeneous integrations in a module, and then you will test again that everything is good. That known good module will go on a board. You test again that everything is good on that module, specifically that the die is still functioning how it should be functioning. And then that will go into a system, and then you'll ship that system to a customer. And when you boot that system at a customer, you're going to run some type of test on the product again to make sure everything is functioning properly. So the point here is that although you test for your known good die at the beginning, there are many opportunities for that die to come bad. And when you sit back and think about it, you keep testing at multiple points in your end-to-end supply chain to keep checking that everything is still working properly. Okay. So the number one thing is, are you able to detect if something is not working correctly? That is the key thing. As you do these mass integrations, you have to be able to detect that something went bad. And here I'm saying something because it might not necessarily be the die. It might be something else. It could be the mounting of that die. It could be a timing problem from die to an adjacent die. Many things can go wrong. Number one, you need to be able to detect it. Number two, you need to be able to diagnose it. You want to know if something doesn't boot properly in my system at final system test. You don't want to be sitting there scratching your head going, oh no, we have a failure. You want to know exactly what failed. Was it a chip that we designed in-house? Was it an HBM that failed? Was it bad integrated circuit, ICT, surface mount technology? Was it a bent pin? Was it a bent connector? You need to be able to diagnose it right away. Otherwise you start wasting a lot of time and money. Ideally, once you diagnose that problem, obviously you're going to fix it, but then you need to look around and go, how come it took me so late to diagnose issue X? Could I have detected that earlier in my supply chain? And you need to look at, is it possible for me to increase coverage up the supply, back up the supply chain to avoid this happening in future once I got this far in my test?
So Zoe, just, roughly how many sort of, known bad episodes, or, how often are these intermittent things versus things that are solidly broken?
Yeah.
I mean,
so that's exactly. So that's a good question. Yeah, everything happens. Yeah, intermittentness happens, and in fact, intermittentness is the worst because one time it's good, next time it's bad, and you can never capture it. Yeah, so that's hard. Solid fails also happen a lot. We get both that happen. The key thing about intermittent is, as soon as it fails, that's when you want to dump as much data as you can around that failure. Because if next time you run it, it passes, you've lost all that information. And you try going back to a supplier with an NTF at your board level, that never works. Yeah, but potentially you do have a marginal part that that would fail later in your supply chain.
And a quick question, do you guys have, I know historically when we were both back at HP, we had a historical thing, but is there a rule of thumb for the cost of failure versus the cost of testing, and where where it's cheaper to find? Or
yeah, obviously it's cheaper to find early on. It's cheapest to find at the die level. As soon as you start putting a die in a package and you're going to throw a package out, then you have the cost of the package. If you have a product, a chip going on a board, you have to rework the board, and that cost of that rework and resoldering a part down and retest does become more expensive. Yeah, and we have a rule of thumb: 3 strikes, you're out. So once you do 3 replacements on any board, you have to throw that board out. So you only have 3 chances to correct a board, and when you have many parts on a board, then you really can't afford for anything to go wrong. Once you start throwing boards out or having to retest boards with flaky parts, it gets incredibly expensive, and it really dramatically slows down your throughput and your ability to ship product to customer.
Thank you.
Yeah. So there are 2 things we're going to talk about today. One is the end-to-end value chain and technically what goes on. The second thing I'll talk about in a couple of slides is relationally what you need to do to build a stronger supply chain. So technically, we're saying, okay, we're operating in this multi-dimensional value chain, and David talked about that quite a bit towards the end, that you might be designing a chip, but you involve many other companies to get your final product shipped. You design your chip, and it might be your big processor, but you're also probably going to procure other components from other companies. Okay, so that's one part of your supply chain. You're going to be interfacing to your wafer fab. You're going to be interfacing to your assembly house, your OSAT, and then your test house. You then have your whole product integration. So you're going to go to another contract manufacturer. You're going to be using other companies to manufacture your boards. And then you're going to be doing various test steps at that other manufacturer. And then you're finally going to do the fulfillment testing, and then you're going to ship your product. So there's many companies and people and teams and processes involved to get any product out. And I say it's not just about the small space that you work in and what you do. You know, as engineers, we tend to design our chip, and then it's like, oh, it goes for test, it goes for bring up, and then if it fails, it becomes somebody else's problem. I'm back onto designing my next chip. If I put a chip on a board and I ship that board to the customer, if I get a customer fail, it's not my problem because I'm on the next part. It's then my RMA team that need to manage it. So there's a lot of people thinking in their own small silos and not really thinking about the end-to-end product. And when you sit back and look, you really need to start to figure how you can influence from the earliest design stage of what is my PDK, how am I going to use it, how am I going to design the chip, through to your chip level testing, through to your board level design and test, and your contract manufacturer that's going to do that to shipping your customer. Ideally, if it's your product and you're accountable to ship that product to the customer, but you're using many other companies to build that product and many other companies' parts, as David said, you're the one that's really accountable, even for other people's bad quality that you're putting on your board, you're still accountable to get that fixed. Yeah, so it's all about this execution up and down the value chain. So I have here a drawing. This is a very high level drawing of really what happens. You know, you start your chip design at the beginning. Use my little pointer here. You start with your chip design. You use a PDK, a physical design kit from the foundry. You do your design and you fab the design. Then you would go through, obviously, wafer testing. And in my mind, this is where the known good die starts, is what gets churned out of the wafer test. You go through various packaging test steps, maybe some system level test at the package level. EDVT is engineering design verification test. And this is where you do a characterization of the system as a whole over high levels, high voltage, high temperature, low voltage, low temperature, to really make sure that this product is robust. And then you'd go into your production flow at the end, in circuit test, probably some type of four-corner diagnostic test over voltage and temperature, a fully integrated system level test, and then you'd ship to the customer. But the point here is, if I start with my known good die here, as it moves down this end-to-end chain, the influences on that die become higher. So I say here, it starts to see a higher number of changes in parameters. And this complexity in emergence theory starts to happen. And we say this complex system transpires when a known good die behavior outcomes are affected by multiple dependencies. So when you test the die at wafer sort, it has few dependencies. It's just dependent on the tester and the wafer sort program. But as you start to integrate that die, it starts to have many more influences on how it functions as it gets shipped into that, put into that final product. And often you do not see, you don't see how that die will function under these other conditions until you get there. So the whole idea is you need to preempt what's going to happen to that die and build that back upstream, ideally to your wafer sort test. But that's not an easy thing to do. It's much easier to talk about it than it is to actually implement it. So here's just an example of what can go wrong. There's many things can go wrong, and it's not just die related. But the problem is you have to sort out between what is die related and what is related to some other process, but it makes my die look bad. And that's the trickiest part, isn't it? Is trying to figure that out. So, you know, right at the beginning here, you have a wafer, you have your design, and then you actually get your wafers. But when you actually get the wafers, they don't always perform how the design simulations said they would. So that's the number one difference. When you put a die into a package, the die starts to see interaction from the package. And potentially if you have multiple die in a package, it starts to see influence from other chip interfaces in terms of not only voltage and timing, but also the thermal, how it behaves thermally can have many different interactions. And, you know, HBM would have one spec, I think it's around like 90 degrees C. Often silicon in a routing product would run at 100 or 105 degrees C. You can actually fry eggs on this stuff. Don't touch it. I mean, I know joking, these things run very hot. So there you have something to deal with right away. I can't put my HBM too close to my networking die because of the thermal issues. As we move on to system level testing, again, the dies start to see more variations in margin. Even as we don't see the full system interoperability, we start to see more interaction from other components and potentially different types of noise and power supplies, noise and things like that coming in. And then of course, when you get to system testing, that die now sees really its first full functional testing. And certainly in networking, it would be full line rate traffic going through every single port. And that's a completely different stress, probably from anything else that that die has seen in any prior test step. So we say here at the bottom, each step widens the interaction of the die in its environment. New parameters and settings can affect that die performance. But you only see that these properties and behaviors only emerge when, you know, all these parts start interacting together. They don't emerge. You don't see that when you test your die. So that's the technical part. And we're all engineers here and we all have our heads buried in the technical work. But having been in this business some time, and certainly from where I sit, I see this whole end-to-end supply chain or value chain that goes on from, you know, the design side of using specific IPs in the design and why those IPs are chosen and used, through to, you know, RMAs coming back on the product maybe a couple of years later. We get to see all the dirty laundry because we do everything in-house. So it's not just about the technical parameters. That's one dimension. The other dimension is what I'm calling, it's relational. It's really at the beginning having goal clarity, starting up front with the end-to-end in mind, planning across domains. By domains, I mean planning across, okay, I have my ATE test. How am I going to system test? If I have this die highly integrated into a package, into a stack, into a module, how am I going to detect if that die or if that substrate or whatever, you know, if something goes bad later? If I'm buying components in from multiple suppliers, I want to be able to hold each supplier accountable immediately for shipping me a part that's not functioning as we believe it should. But you have to, so you have to really be designing for test on your system from day one and not leaving it to a retro thought after you have your issues. So you need to plan across domains. You have to build a common language because chip designers don't always talk around system level testing. Often chip designers don't even understand the ins and outs of ATE testing. Yeah, so you have to build a team of people that really can speak a common language up and down the supply chain. That person has to be credible. You have to show up with, if you don't do this, this is what will happen. And I have an example here, and you don't want to end up like this product. You have to show up almost with your scare tactics of, this is why you need to do it, guys. It takes your time, but you will reap the reward once you do this. You have to sell a proposal. You have to build that guiding coalition, build those relationships of functions from IP, from design, product development and quality and reliability team to co-optimize the performance and the time to market and the cost. So we're trying to orchestrate cross-functionally. We're trying to define shared metrics with the end product in mind. And we're trying to enable data flow from one test step to the next test step to the next test step, from the final test step back up to the other test steps, to co-optimize processes and to really try and do correlations of the life of the die as it goes down into its module, into its product, into its system, into its boards. And use these data analytics to really try and potentially predict when a die goes bad. If a die does go bad, what happened? Was it the die? Was it some other process? If it was the die, where on the die? Was it the memory? Was it the logic? Was it a SerDes? And if it was a SerDes, which port on the SerDes? What happened? What pattern was running? Was it a pseudo-random pattern? Was it my traffic pattern that I ran? So you really need to debug to that level from day one. If a memory failed, if you have an integrated memory, an SRAM that failed on your die, I want to know at that point of fail exactly which instance failed. And if I get 2% of memory fails in my product, if I can isolate to exactly which instance failed at the time it failed and run data analytics, then I guarantee 9 times out of 10, you'll see it's always the same type of memory that fails in a similar place. So you know automatically, I have a systematic issue with my memory. You'll never see it at wafer sort. Of course, it's going to be NTF because it's probably a test escape. It's a marginality that you don't see until that part starts to run the application in its native mode. So data analytics is huge, and we're on the edge of data analytics right now. It's sort of the Wild West out there of how you do it and the databases that you use and what you use in the cloud. And it's a highly interesting area. It's a big area, and I think it's really the future to, you know, it's going to be a whole nother step to producing a whole nother level of the ability to have known good die.
So, so 2 questions that we received that tie into what you were just talking about here. You know, one is, you know, with the data sharing and across the supply chain, it's a challenge to the business relationships. David talked about it a little bit. So the technology is less an issue than the transparency, and the person was asking, can you comment on what's needed to change those relationships to get more data and more sharing and transparency?
Yeah, so yes, you're right. It's always a challenge. I think number one is the business. A lot of it is a business relationship, and it's trust. Yeah, you have to build trust with your partners. I think everybody wants to produce the cleanest die. So that really is like your starting point. Nobody wants to ship bad die. Everybody wants to really test it, because at the end of the day, it's profit, isn't it? If you're testing shoddy die, and I shouldn't even say that, yeah. If you're testing marginal die, it becomes lost revenue at the end of the day for everybody. So I think it's building trust. It's really showing the value of the data, and that when you share data, how much quicker it is to drive to root cause. And, you know, we're always on, it's the engineering, it's the technical side versus the business side. Don't invite the business guys to the meeting, because I need to have just a technical conversation about getting this fixed. Yeah. So yeah, it's not easy. A lot of it's around relationship. You know, some suppliers really don't want to share data, and you have to be cognizant of that, and you have to build potentially a process where you're not going to get specific data, and make sure then that you can feed your data back, but you might not get anything back from a specific supplier. They might just take your data and say, oh yeah, we found a problem and we fixed it. And you have to go, I hope so. Yeah, so it just depends, but never give up. Yeah, but do build those guiding coalitions. It's very valuable. And so there's a couple of things here. One is you have to continue to drive for diagnosis. One is for which parameters are going to help me the most to drive the diagnosis? And secondly, what data do I need for that? So parameters, it's the usual suspects, isn't it, of power. Power is a big factor. Power can really vary die to die, test to test. You need to understand how your chip draws power, what's the power integrity, what's the thermal mapping across your die and across multiple dies. Measuring on-die voltage is key, not just one time, but at specific points of your testing or your application is key. Understanding noise margin, understanding, do voltage bins help anything? You know, where I can scale my voltage depending on perhaps the speed of the die, or the you know, what my application needs are. I can voltage bin and change my VDD setting. You have to be very aware of signal integrity as you put your die into a package, into a module, into a board. If you're running thousands of, you know, 56 gig PAM4 ports, signal integrity can become interesting. You have to keep that eye clean. So you need to be really looking at everything as you're integrating that die into the product. And there's many things here that you have to be looking at, particularly if you're looking at data. Yeah, continually you must log data to get fault isolation to the die and sub die level. You want to log data to show potentially, do I need to do margin matching from chip to chip, board to board? Will that help increase my product yield? Keep an eye on thermal noise measurements, log whatever you can around those. Make sure that you always have reliability compliance from your reliability testing and your product specs. And certainly in networking, there are very strict compliance around power and the actual noise, the actual physical noise that you hear from a system that can dictate what goes on in your product in terms of voltage and power requirements. Key here, like say wafer sort data, you're going to log as much as you can. Do keep feeding that back to the foundry to improve process target and your yields. Create data to figure best matching for voltage and power. Sometimes matching dies really helps with your application. It helps you to reach your specifications. Alluded to this already, voltage and noise margin must comply to your system power specs. And yeah, thermal resistance mapping to identify compliance with other dies. So there's many opportunities here to be monitoring and logging data of your dies, multiple dies, and your product right through its life cycle. So at this point, I'm going to hand over to Yuri, and he's going to talk into a little more detail around these areas and give some more examples of areas to improve and areas to collaborate.
Zoe, quick question before, or as we're handing off. It seems like there's a big possibility to over engineer and end up with a very expensive product. Do you ever reconsider and think about harvesting and cost down?
Yes. Yeah. So of course, over engineering, yes, nobody wants to over engineer, and because that is time and money and margin, isn't it, when you over engineer? So you always want to do the minimal that you can get away with. However, you know, it's certainly in networking, nobody wants to ship a product that's going to go down and you're going to lose your network connection. So you must have a lot of reliability in networking. So a lot of thought is put up front into testing. A lot of hooks are built in. We're constantly looking at, can you build in more hooks, and what specifically should those be? So hooks that are built in are very relevant to product test, and they will be used. I think, you know, as always, even in system level test, you start off with, I wouldn't say we even start off over testing, but we start off with significant testing to ensure good shipping of product, but almost immediately, as in die level test, you start taking tests out that constantly pass to reduce your test time.
Got it. Thank you.
Okay, so in the second half of the presentation, we will dive into how we will leverage these new parameters to speed up our learning and system development, and we will refer to complexity theory to enhance characterization and to data as the communication media and to end-to-end supply chain. And we will apply that to how to build a more cross-functional supply chain and organization. So as Zoe mentioned, we have more parameters we need to take care of as we move from components to the system. And the complexity of the system is not growing linearly with number of parameters. We're adding to that interaction and nonlinear interactions. And turns out that by adding more terms to the model, we could get into new properties. In the complexity theory, they call those properties like emergent properties. An example to that could be as we move from single ant-to-ant colonies to from the cell to tissues, from the single human to the groups, there could be an emergent property, which is a self-organization. When we just ride the bike, we have there is a rotational movement of the wheels and a rotational movement of the pedals, but it translates to the new property, we move ahead. So if I dive here to the characterization of the system as it is, systems as those are kind of prioritized or ranked by complexity, bringing here an illustration of some 9-level representation of complexity from 50 years ago from an economist from Chicago Booth School of Business. So he looked at all the systems, and we could say we have systems which have a static parameters, then parameters or properties are starting to change over time. Then we add stochastic properties, we have feedback loops. This is first three levels. This is where we deal mostly as an engineers. Then there is a more complex system, a life system. And at the end, at the level 8, we have an organization. And he even reserves the level 9 to a complexity which is still unknown. So today, in today's systems overall, we definitely operate more into 3 levels. And sometimes with artificial intelligence, we touch level 6 systems. But what I'm trying to say here is that we move from the components to the system. We definitely make more complex problem on these first 3 levels. But we also are touching here the organization. So organization that deals with the system is also more complex, and because we deal with more suppliers, we do more complex supply chain and more interactions that are across sub-industries. And those interactions have built-in problems that this organization has to tackle, because each sub-industry has their own decision-making process. There are people with different educational background, and we need to bridge that. And that is where the more sophisticated organization needed to break inter-domain boundaries. So back to technical here, what we're saying, we have a system that has many components, and we could define each component as a node, and then we want to represent an interaction as a link between the components in the model. And we will try to capture here how do we characterize those interactions in a more technical way. So if we break our system into domains, like 3 domains for simplicity, we have foundry with the process, we have design house that is doing component design, and we have a system that puts all those components on a board and integrates that with the software. So there is the major boundary comes from this, the major new properties are coming from the system. In a very simple way, we have a system related failure mode. And we from one side, we want to capture that system failure mode early on. And for that, we need to have, we often use system level tests that actually takes that task and moves it on the component level. And we also want to be able to characterize this failure mechanism properly on the system, because it really depends on the environment that is in the system. And we also want to characterize how this failure mechanism really, how this environment on the system impacts the process. We also need to characterize the part of the environment is the cooling. So we want to have a better simulation and characterization of the cooling. A part of the environment is how power supply could manage shifts in the load and the noise. It's another boundary and interface on the system side. So we are addressing that with a better measurement in the system environment, and we are also trying to build a test methodology with better fault isolation that would allow us on a system level to go down, as Zoe mentioned at the beginning, and connect the failure mode to specific circuits in the design, and hopefully to device performance, and give feedback to the process. And the third aspect of the interactions is that we want to ensure the performance matches our specs across the lifetime of the product. So we have a degradation model, and this degradation model is also influenced a lot by the system environment. So the other property here is how to characterize the impact of the system and the environment on the degradation on the degradation model that we use to set up the right carbon. For that, we need to have a better characterization, and we want to move from a generic margin that is very expensive for us to more custom margin that is just enough to give us the right quality at the right cost. So high level, how do we characterize this interaction? If we have the built-in fault isolation and environment measurement, we have a better foundation to take the specs that we have on the system under the system environment and translate it back to design and translate it back to foundries. So that way we could build a more accurate model down supply chain. At the same time, we are aware that we cannot, on a design level, we have a limited capabilities. And as we develop a product up, to supply chain, we may get to some unexpected properties or some unexpected parameters that exhibit low margin. And for that, we want to be able to propagate this marginality from the circuit, from the design to the system, and update our model accordingly. And we're talking here about updating the performance model, silicon to simulation model, and updating our yield model, and updating our reliability model. Okay, so that translates to those interactions, and those translate to maybe three emerging properties that are related to known good die test and a concept. One is that we need the good foundation will translate here to more accurate models. More accurate models will allow us to break the system into different failure mechanisms. And this failure mechanism could be share the information on the model level and on a characterization level could be shared with stakeholders. It could be stakeholders that are internal to organization, it could be suppliers. And as we have data there and a mathematical representation, it creates a connection with our with stakeholders. It basically enables this end-to-end supply chain that Zoe mentioned in the beginning. So in this case, we want to connect better and share data and fault failure modes and fault isolation information with the foundry, with cooling, thermal design, with power supply design, and with our software partners to make the tests that they write for the system be more aware about of the failure mechanisms that are system related. And the third straightforward emergent property here, when you have a good model, you have information on the failure mechanism, and you have data, you could map for each issue that you have, you could map what kind of impact we have. And when you have an impact, you could apply Pareto approach, and you could address bottlenecks and major system constraints in a more planned way. You could manage better your resources and to speed up this learning cycle. Okay, so as we mentioned, as we have a better modeling and we have an interface across the different failure mechanisms, so we are collecting more data. So we could start building our data concept here with the component yield management system, and we are adding to that system level data. We are adding to that supplier data, and we share certain portions of our data and supplier data focused on the specific failure mechanism across all stakeholders. So we could use cloud hosting, and it makes it easier to exchange the data. We can integrate different data types in the cloud, And we could leverage that, the whole infrastructure, to also enrich the data, not just giving just production data, but we could share characterization data, pilot data, and even data from the field, because we have this capability here to break the data down to certain subsets that are relevant to certain stakeholders.
So Yuri, is just a quick question. I mean, is this data all structured, or I mean, is this just like, you know, the system test failure log, and then somebody has to structure it to be meaningful to the rest of the supply chain?
Yeah. So that is an important piece. In my maybe simplistic view, I see that the more structural data here, we could apply more structure to the data, and that makes it easier to integrate across different data types and break it into pieces. So that is more straightforward approach. But we definitely, if something that we could not structurize, we could leave it as an unstructured way and apply different mechanisms of learning. But maybe practical examples here, I have in mind mostly structural representation.
Okay, thank you.
Okay, and how do we map it back, all that to the philosophy of known good dies? So we need to ship a known good system. For that, we need known good modules, packages, die process, and incoming material. So we kind of apply known good die philosophy to every stage. And it all starts with a more accurate model, with more accurate specs. Then we add to that data, then we add to that exchange and better collaboration with partners through end-to-end approach. And we use data here to break these communication barriers between different suppliers and different sub-industries. So that is a major message here. And maybe at the end, we believe that there are three areas that are kind of developing very fast to provide more tools to that specific challenge. One is that we have tools that would cover components, would cover silicon design, would cover thermal, would cover noise. And we have basically different design abstraction models. And we see recently those models are integrated by EDA companies into more system level simulation environment. And we see as that becomes more mature, we hope to see the way that we could kind of connect our data and update our models as we learn and develop the product. And we're looking for more collaboration with EDA guys in that area. Another area that is developing fast, as we mentioned, the environment in the system is different than environment during our test. So we believe that the all-on-die sensing that happens and works in the system is developing very fast. And it includes sensor design, it includes how we place the sensor to provide the coverage, and also how we process the data from those sensors. And then the third one is we have these additional models and additional data. We want to also map it to degradation over time and come up with a more accurate degradation model that will allow us to break the generic model that they were getting from the foundry to work for in the environment of the system that we have. Okay, so again, we talked about more accurate model, more coverage of the failure mechanism across different stakeholders, data collaboration, and building basically more efficient organization and supply chain to improve our learning cycles. Thank you.
Wow. Thank you, Yuri. Thank you, Zoe. Lots of questions, but first a high level question. I mean, so you're talking about this philosophy and approach. How far are you in implementing this? Do you have indicators of success going in this direction yet?
Yeah, I'll take that.
Go ahead.
How far are we in implementing it? We have pockets of success. Let me put it that way. Yeah, to get total end-to-end integration is like a mammoth task because there are just so many individual parties involved. And back to your question, Ira, about the data. Yeah, you know, we're looking at disparate data formats of what comes out of ATE and what comes out of System are like from different planets. So it takes a lot of not only saying what data I want to log, how am I going to log it? How am I going to get the chip to log that out? But then what format are you going to log it in? And then being able to grab that format and feed it into your analytics, whatever software on your cloud is all a huge, huge, huge task. And it takes a lot of time, and it takes a lot of that, what we talked about, orchestrating up and down the supply chain of this is what I need. This is why I need it. This is why you need to work on it. So it's a mammoth job. It's not coming quickly and easily.
Understood. But it's, yeah, you know, you obviously have a direction that you want to head, and so it allows you to build a framework and then and try to collect and improve the process. There are probably more questions than we have time for, but let me ask 2 or 3 here. When this one, how effectively and to what extent is SLT integrated into your production test flow? And are there constraints in terms of test time and complexity in developing the SLT test? And let's be, I believe this SLT question is when you take the package part and put it in a system level test versus when you're doing, let's say, a board-based test in your product test. I mean,
Yuri, do you want to answer, or should I answer?
Okay. So what are the challenges? Yeah. So you want to build this SLT platform that would allow you to run those patterns that represent performance in the system. So you need to build in the right hardware, and you need to have a good software organization that knows how to translate the pattern to this environment. Also, you want to monitor that and measure the environment in this SLT to make sure it matches what we have on the system and it runs correctly. And then another challenge is that you want to put it in this manufacturing environment and achieve the target test cost and make it repeatable and working on the test floor.
Understood. And then you guys didn't really touch on built-in self-test and the end-to-end context. I mean, so how important is it? How useful is it?
Yeah, so I think built-in self-test is the key, and the key is designing in optimal self-test of this is what I need to test this part, and this is what I'm going to design in. So it's not just anyone's built-in self-test. Yeah, it is highly optimized for the issues that we see. But certainly, on the contrary to that, things like memory BIST are key. Yeah, that you need to run memory BIST all the time, because not only does memory play a key function, certainly in networking products, but memory BIST runs the memory completely different from how the memory is used in the application. So there are definitely gaps there. So memory BIST is key, and constantly fine-tuning the memory BIST and fine-tuning product level memory test is something that is a continuous project.
Right. Well, I thank you both for a great presentation. We will make sure the slides are available by next week on the website, and the video will be posted as soon as we can. And you'll see the links on the website. So thank you again, Zoe and Yuri. An excellent presentation. Thank you.
Thank you.
Thank you.
This is the end of this session, the first session of the Known Good Die Workshop. I'd like to thank our sponsors once again who made this event possible, ASE Group, Advantes, Gelpack, Moldbauer, and Omcor. ASC, as our diamond sponsor, is an OSAT, providing design, assembly, test, materials, components, and logistics. Advantest, as a leader in the ATE industry with over 30,000 installed systems and over 60 years of experience in measurement. GelPack, whose expertise is protecting the world's most valuable devices in terms of shipping and handling. And a Mulbauer Group, specializing in factory automation and data integration. So I'd like to thank our sponsors. I'd like to thank everybody for attending. I'd like to thank our presenters. Our next session, session 2, which will be the strategy discussion, will start tomorrow, September 17th at 8 a.m. Pacific and run to approximately 10 a.m. So I want to thank everybody and wish everybody a good day and look forward to seeing everybody online tomorrow. Thank you.